Ok. Questa è la seconda parte della lezione di 18 novembre. Vorrei chiedere un attimo, ok. Vorrei chiedere se avete qualche domande collegate con, certamente questa identità cercheremo di dimostrare tra poco, ma prima di dimostrarla forse vorrei dare un'idea con un esempio semplice per vedere come possiamo utilizzarla. Ecco l'esempio, abbiamo detto che abbiamo esempio. Let's switch to English. Okay. Our first example concerns the following question that we have, for example, omega is set of n equal 100 people. That is part of population in small village that we examine. And we divide these people in, for example, today we measure all these people and we can say U1 is set of infected people. They're coronavirus positive. They have positive test. And U2 is the set of negative. Let us suppose this set has, I shall clean also this line. Practically what we need is bias formula. So U1 shall be of 80 people, U2, no, it's opposite, 20, and it shall be 80. So 1/5 of the population is positive to specific virus. Let us not use only coronavirus, but in general, we have specific virus, we make this study. Then, what we know, what we want to compute. We know that the event we are asking is that we have to measure the people that are in hospital after 1 month. By definition, to be in hospital meaning that the situation is very delicate, they need special treatment, while positive people, they can moment stay also in their houses. We know the real situation. So question is to so what we know is following probability a guy is in the hospital when he is already positive, let us say, is 1/2. While the probability the probability that the guy is hospital when it is not positive, either is negative, shall be 1/10, for example. And the question is to the following. What is probability that a person in the hospital, that is in the hospital, is in the group of positive measurements that we did now? So the question is, what is probability that a guy that is in hospital actually is in the group of positive persons? U1. So the doctor is going to the hospital, sees one guy who is in very bad conditions, and is thinking, so what is probability that this guy had already positiveness 1 month ago, and what is probability, complementary probability shall be to be U2 under the condition this guy is in the hospital. So you see how important is this relation, because enables immediately to plug into our formula the needed numbers and compute this probability. How we shall compute? Applying this formula. Of course, I need space, I need to write bigger letters, therefore I have to clean something. But before cleaning, I want to ask you if this example is clear, if it is clear what we know and what we need to compute. Okay, if this is clear, I shall clean this part of the blackboard, because this decomposition already is formally bias already is written. So we are starting to write here P of U1 under V. Of course, we shall need also P of U1 and P of U2, but P of U1 is clear. This is 20 divided by whole numbers. The fact that a guy is positive is 20 divided by 100, is 1/5. And probability U2, that a person is negative, is 4/5. And we apply this formula. So we put P of V U1 multiplied by P of U1. Here I have to divide P of V U1, P of U1 plus P of V U2, I need small space, times P of U2. And let us continue. What is probability V of U1? This is 1/2. P of U1, we set 1/5. Below, we have the same guy, 1/2 by 1/5, plus what we have, P of V U2, 1/10 times P of U2. This is 4/5. Let me ask if this substitution is clear, if you have some question, because I simply took my data and plug inside the Bayes formula.
Professore, il divisore, la somma con le probabilità condizionate risponderebbe a P di V, sarebbe la probabilità dell'evento V.
Sì, sì.
Okay.
Okay, we shall see this property. But before, let us apply as it was written the formula. We have this formula, so I apply it simplifying. I simply put in the form that is. Now let us compute this. So we have 1/10. Here we have 1/10. Here what we have, here we have one half is 1/10 plus 4/50. This is 9. 1/10 divided by 5 plus 4 is 9/50. So this is 5/9. Let me check if you agree with my calculation. You see, probability that the guy is in the hospital is all infected is more than half. So very high probability. Can you confirm that my result is correct after applying the bias formula?
Yes. Yes. Correct.
Okay, so we have provided that we have the formula. Now, try to check the formula. But before going, I plan to clean the whiteboard. Do you have some questions for the application of bias formula? Of course, the situation can change. You can have different situation. I choose something different from the book because I follow the book that I suggested in my homepage. The book is connected with other cases, assurance, change the real life application. Always the question is to have such a relation. Okay. Let us try now to understand this formula. In very simple way. To see that this formula is true when we have division in two sets. So when we represent omega as U1 union U2. So what we can say? We can say that U2 is the complementary set of U1. Therefore, there is a nice relation between P2 and P1. Here we can say P of U2 is 1 minus probability of U1. So if you need, we can use also this relation. Okay. So we take our omega, we divide into U1, U2, and then we take our V. It is clear that we will have part that is in U1, but also part of V shall be in U2. Okay, see what we have to prove. Let us, for example, compute P of U1. What was the definition? According to our definition, this was probability of U1 intersected with V divided by P of V. This was our definition. When we take our definition of P of V with Uj, let us recall us what was the definition. This was P of Uj intersected V, but our J is 1, so we don't care here to be divided by P1. So when you multiply, when you take this product, I shall put this guy here, put P of U1 by this. The result is simply this guy. Therefore, we can say that numerator here is exactly equal to the probability of U intersected with V. What we can say about the numerator? For the numerator, we can say V is, first we take V intersected with U1, the blue part, and we add V intersected with U2. It is clear the blue one plus red one gives me the whole V. So what we have downstairs in the denominator is simply connected with this relation P of V. Have in mind that blue set and red set, they are disjoint. When you have disjoint sets, probability of the union is simply the sum of two probabilities. So we have P of V intersected with U1 plus, I shall add here, P of V intersected with U2. So now you see our whiteboard becomes kind of mosaic. All pieces to prove the relation are here, and we only have to order and make the conclusion that this is true. To make this conclusion, let us for the moment call this relation 1. This is the definition. The second one we shall call 2, also following from the definition of this conditional probability. And then we have the important relation 3. Actually, I shall make small modification in my relation 1 because this relation is irrelevant whether or not I use here 1 or 2. That's why I shall put here kappa. When kappa is 1, is one relation. When kappa is 2, is another relation. But you see what we have in denominator if you use combination between 1 and 3. Since I need a little bit space, the final conclusion I shall write on the blackboard, and I shall clean only the picture. So all other pieces of the mosaic shall be on the white. So if you take 1 plus 3, I assert that what is written here in denominator, this is exactly P of V. In fact, according to this, when I take kappa equal 1, this guy here is also here. We could put U kappa, U kappa, U kappa. This is irrelevant if we take U1 or U kappa. If you take this product, probably it's better to refer to 2. If we take this product that is in the sum, we take probability of intersection. But probability of intersection, if you take the sum, gives you probability of V. Therefore, let us call this 4. Right hand side of 4 is equal. I do not write due to lack of space. I am writing right hand side of 4. You look here. Is equal to what? Later, according to 2 is probability of V intersected U. I think we take J equal 1, I think, but we can keep J. This is Uj. Up. If I apply this guy with kappa equal J, I take numerator this. Denominator is, we said, this guy, due to 2, is probability of U kappa intersected with V. When you take the sum, probability of V. So, hand side of 4 is this guy. But this guy is equal to the left-hand side of 4 by definition, by our definition. And the proof is finished. Here we have shown that 2 plus 3 practically proves that right-hand side is transformed in the left-hand side, because this here is exactly the definition of this conditional probability. Let us see on the blackboard the scheme. 1, of course, implies 2. 2 plus 3 implies this relation, and this relation implies what we needed to prove. This is the end of the proof. Let us see if you agree with our reasoning, with what is written on the whiteboard. As you already observed, this denominator is simply probability of V, but this was used in our proof, and practically was the key point, while numerator is simply probability of V intersected with Uj. And this, of course, this quantity is our conditional probability. There we have an example. We have the bias formula proved, and I am waiting some of your observations, and of course we can create much more examples, but I think one example at least is sufficient. In the future we shall have further exercise on this topic. Okay, if you haven't more questions, we can say that the same works if we have three sets. What is the difference? The fact that when you have three complementary sets, here you shall have this union with V intersected with U3. And therefore, if you have n sets, you generalize this, and always the denominator is probability of V, while numerator is probability of V intersected with U. And therefore, the bias is possibility to have one conditional probability and connect with opposite ordering conditional probability. As we already mentioned, some problems connected with application of probability theory requires more sophisticated ordering of choice of our probability function. Till the moment, what we had in our discrete setting, we said that our set omega, algebra of subsets, events are, and we have P, the function probability that to any element of this algebra associates number between 0 and 1. But in all our examples, we have equidistributed probability. What does it mean? If you take a set that is formed by only one element, of course, we are speaking about finite omega, and in this case, we speak about discrete. Always when you take one set, we say probability of this one set is independently of our choice of this element, 1 over number of elements of omega. So it is independent if we speak about person, this guy is, how to say, young, but we know very well that some probabilities depend on the age. Therefore, we can have, for example, our omega, that is x1, for example, xn elements. And when you take one element set xj, and when you measure its probability, nobody says you that this should be 1 over omega. We can say that this is some number, pj, of course, 0 and 1. And what are the properties of these probabilities? We need for them to have sum of pj, j from 1 to n, should be exactly 1. Therefore, equidistributed probability space has for one element sets fixed probability that is independent of the choice of this element. In the real situation, this, for example, will depend which is this person. If we order the persons according to the age, we can say probability, for example, to have complicated treatment during the virus, disease during the disease is higher when the age is bigger. Therefore, probably if you have n equal 3, if you divide in some sense your group in 3 main ages, and if you take one of these ages, you can say 1 is, for example, 1/10, youngest group, P2 is 3/10, then I am asking you what remains for P3. Since the sum of all P should be 1, what remains is 6/10. Therefore, this is not equidistributed probability space if choice of the function of probability function is not independent of the choice of this element. Somehow, till the moment, all examples considered equidistributional probability. For this case, we have to know also to measure whether or not, this is important question, we have independent events. So, to have some example, you can say that one event is that fixed person P, has age above 30. This is one event. The other possibility, age smaller than 30. And we have 2 events. On the other hand, you can say, okay, another event should be the person, for example, let's switch from the health to the salary, because salary is probably something better to be accepted. Too many diseases. Let us switch. For example, salary of the guy is bigger than 2,000 euro. Salary is smaller or equal than 2,000 euro. Of course, here you have one event. Say this is the set of all people with age bigger than 30. We can take our group of, for example, people in fixed city and say people with age bigger than 30. Okay, this is if a guy is with age bigger than 30, this is one event. If a guy is with age smaller than 30, this is another event. For the same guy, we can ask his salary, for example, is 0. He is not working, so he is in this set, or his salary is bigger than 2,000. For example, what is one event? U1 shall be age smaller than 30, and V is all people with salary bigger than 2,000. Are these 2 events independent? Actually, we didn't give a definition of independent events. Intuitively, you can say, oh, there is kind of relation between the age and the salary, so it is not quite independent. But how we shall check? Probably in some city, imagine on the moon. On the moon, the 2 events are independent. how we define independent events. And the definition is very simple. We have two independent events, and V are independent. When you take probability of U intersected with V, this should be probability of U multiplied by probability of V. This is the test. Let us see, first of all, one example. The case is, before going to this complicated case, because here is slightly more complicated, let us take one example. Our example is with one dice. We can take U means the exit of drawing one dice is 2 or 4, 2 or 3. Poi, let's say, the exit is even number. Let us check if the exit of drawing one dice to be 2 or 3, and this even to have even number, if these two events are dependent. So we have to compute U intersected with V. What is U intersected with V? The exit is 1. Even number, and to being 2 or 3 means exit is only 2. What is the probability to have exit 2 drawing one dice? Of course, its probability is 1/6, because when you have a dice, you have 6 possible results. Let us compute probability of U. What is probability of U? You can help me. How many exits we have?
1/3.
We have 2 possibilities. 2 divided by 6 is 1/3. So this is 1/3. We draw only one dice. So if the event is to have 2 or 3, we have 2 possibilities. All number of possible exits, possible results, 6. 2 by 6 is 1/3. What is the probability of V?
One.
Yes? It is? Sorry, I didn't. 1 or
1.
1? When you draw your dice, even numbers are 2, 4, and 6. So you have 3 exits divided by 6. This is 1/2. Sorry, probably something in the connection was not good, because I couldn't hear well. It was stopped. You want to say 1/2, or I am mistaken? Yes, okay. Let's, please. Yes, yes.
No, I was wrong.
Okay. This is 1/2. And let me ask you if our test is okay. 1/6 is 1 times 1/2. So these are 2 independent events. When you have concrete example, you can check whether or not these events are independent. When your data says you it's true, for example, if you measure with statistical data, you measure how many times happens event U, how many times event V, then you measure how many times happens U intersected with V, and then you show that your statistical data show this is not true. Of course, this has to be dependent. And we know that in this case, we have dependence. Independence means we have to check this. So this seems to be the essential part in our statistical, in our introduction to probability. And with this, finished the part that is connected with equidistributional probabilities. Therefore, he assumed always that a set of one element has exactly probability that is independent of the choice of the element in this set. Okay, what shall be the next plan? Practically, we finished section 3. Here we have several exercises in the book. We can, for example, see some of them. But after this, for example, probably we can take one simple example of the book. That is...
excuse me.
Yes?
If in the problem it's said that we have 2 independent events, and I have to calculate the conditional probability, I can use the formula that we use to demonstrate that the independent events are in.
Yes, we can combine, but I prefer to give only the definition of independent events, because if you put in denominator P of U, then you can rewrite this guy as P of V under the condition U, if this is equal P of V. You can rewrite using the conditional probability this definition in this way. And this means that probability event V happens when U holds is independent whether or not U holds. So you have the same probability V. And this also can be used as interpretation of the definition of this is equivalent relation. And probably you can add also the other possibility. Probability of U under the condition V is exactly the probability of U. So you can exchange the roles of U and V, and the equivalent to your original definition. All these variants can be connected or not with conditional probability. So thank you for this question. In this way, we can connect conditional probability with independent events.
Thank you.
Welcome. Now, let us take one exercise from our book. This is exercise number 12. That I shall write on the white. And we can discuss, at least to start, discuss its solution. Most exercises are trivial applications of the definition and properties we discussed. So this is quite easy, but probably this exercise is slightly more creative, and that's why I should devote, I think, very short discussion connected with this exercise. So, okay, we are ready. Actually, this exercise says that probability that here they use other letters, but U, V, A, F, this is not so important. They assert that intersection between two sets in our algebra always is bigger or equal than probability of A to probability of F minus 1. So they are asking in exercise 12 to show that inequality always is true. So this, in some sense, is connected with the following picture. You have A, F, then this guy is the intersection. Actually, it is connected with De Morgan formulas. We know that A union F complementary set, according to the Morgan formula, what was this set? If I have union after complementary, this becomes A complementary intersected with F complementary. This is De Morgan. Okay. We have this. So let us put what is probability of this guy? Probability of complementary set is 1 minus probability of A. This is also due to the definition. Actually, the property of our probability space. Now, if you use De Morgan rule, we know another important property, probability of A union F. Of course, when AF have empty set intersection, this is probability of A, Q probability of. If instead we have intersection in the union, we count this set in this sum twice. So here we have to add minus probability of A intersected with F. And these are three relations that we shall use in order to prove this inequality. Let's call this one. This is 2, this is 3, and this is 4. So we shall say that these three relations imply this one. How do this? Of course, if I take probability in 2, 2 implies probability of complementary set, probability of A union F complementary set. This is 1 minus probability of A union of F. This is due to 3. But for the union, we can apply this formula. So I substitute the union with this guy, and we get 1 minus P A minus P F plus P A intersected with F. And we are done. Why? What does it mean, 1? If I put to the left-hand side everything, means this with minus, this with minus, this with plus is bigger or equal than 0. But what is this expression? This expression is here. This is probability of this set. But bigger or equal than 0, this is always true because any set is always bigger or equal than 0. And in this way, from this, we deduce 1. So 2 and 3 implied this relation. Here use 4, and then we get 1. This is the solution of this more complicated problem 12. Let me ask you if you understand this solution, if you have some. This is a little bit more mathematical. I wanted to solve, I think other examples are more clear and simpler in the book. And we shall add also different examples. But this is application of the Morgan formula and this simple rule that A intersected with F, union with F, is equal practically F union A minus A intersected with F. Look what we have here. Intersection is, we take our the union is F, and then we take this piece. So we use this relation, and now we can see that this guy and this guy, they're complementary, and therefore apply the formula for the measure of this guy shall be the measure of this plus the measure of plus the probability of this space. And probability of this space, again, we have here the difference of two complementary sets. Therefore, this relation, I think, let me check, did we discuss in the past this relation for? We shall repeat it in the next appointments with you. This is part of the Morgan formula. Remember, if we have this, we know that when intersection is empty, this is true. But I don't remember if we consider the case of non-intersection. So probably the next time, please to remind me to discuss formula 4. Okay. With this, I think we can stop our discussion today. We have many lectures today. And tomorrow, the next week, we shall continue on Tuesday. So thank you for your attention. Let me stop the record.